Hi everybody! In this video we are going to talk about interference of light. In this photo there is an interference of waves. One is caused by mechanical waves, interference of water, and the other is caused by light, which is the subject of our lesson. At the end of this lesson, the student will be able to know the phenomenon of interference of light, know the conditions of obtaining interference fringes, interpret the formation of interference fringes, and give the expressions of the path difference and the interfringe distance. So we are going to start things off by defining interference, which is a phenomenon that occurs when two waves interact with each other. By definition, interference is the superposition of waves having same nature and same frequency. In order for interference to take place, two conditions must be satisfied. The first one, light emitted by two sources must be synchronous, which means same frequency or same wavelengths or same color. So, if we take the regular light as an example, this light consists of many wavelengths, so it is not synchronous, while when we put a red filter in front of it, then this source becomes synchronous. The second condition, light emitted by two sources must be coherent, which means the two light waves have a constant phase difference between them. So, in the first two figures, light traveling in different phases, so they are incoherent, while in the third figure, light traveling in phase, so it is coherent. In 1801, an English physicist named Thomas Young performed an experiment that explained the interference of light. He performed the experiment using a candle flame, which is a non-synchronous and incoherent source. So he used a color filter to make the light monochromatic and so synchronized. And then he used a narrow slit to make it coherent. In front of the single slit, he placed a double slit S1 and S2. The two slits act as two secondary coherent and synchronous sources to satisfy the conditions of interference. In Young's experimental setup, a laser source of light illuminates a double slit as indicated in the figure below. S1 and S2 are two slits separated by a distance A, and the distance between the slit and the screen is D. The diffracted rays emerged from S1 and S2 interfere on the screen in a region called region of interference or interference zone. Now, what do we observe on the screen when interference takes place? We observe an interference pattern composed of alternating bright and dark fringes that are rectilinear, equidistant, and parallel to the slits. Now let's try to solve this application. Consider the three experiments below. S3 and S4 are point sources of red monochromatic light, while S5 is a point source of blue monochromatic light. S1 and S2 are two fine and parallel slits. Specify in each experiment whether an interference phenomenon takes place or not. In the first experiment, S3 and S5 are not synchronous because they are of different colors, and they are not coherent because they are different sources, so no interference takes place. While in the second experiment, S3 and S4 are synchronous since they have same color, and not coherent because they are of two different sources, so no interference takes place. In the third experiment, S1 and S2 are derived from the same source, so they are synchronous and coherent. So in this experiment, the interference takes place. Let M be a point belong to the interference zone of position xm. The optical path difference delta M at point M is the difference between the two optical paths SS2 M and SS1 M, which is equal to SS2 plus S2 M minus SS1 plus S1 M, equal to SS2 minus SS1 plus S2 M minus S1 M, which is equal to SS2 minus SS1 plus D2 minus D1, where S2M equal to D2 and S1M equal to D1. But D2 minus D1 equal AX over D. The derivation of this formula is not required, and SS2 minus SS1 equal AY over D. Also, the derivation of this formula is not required. Finally, delta at point M equal to AY over D plus AX M over capital D. Now, if S is placed at the perpendicular bisector of S1, S2 as shown in the adjacent figure, SS1 equal to SS2, therefore delta at M equal to D2 minus D1, which is equal also to AX M over D. Now let's discover the reason behind the formation of bright fringes. If we look at this figure, we find that the two waves reach at point M in phase. In this case, the interference is constructive, and so a bright fringe is formed. So the reason behind the formation of a bright fringe is the superposition of waves that are in phase. And the optical path difference delta of a bright fringe is delta for the bright fringe equal to k lambda, where k is an integer. While in the case of a dark fringe, the two waves reach point M in antiphase, and the interference in this case is destructive, so a dark fringe is formed. Therefore, the reason behind the formation of a dark fringe is the superposition of waves that are antiphase. And the optical path difference delta for a dark fringe is delta equal 2k plus 1 lambda over 2, where k is an integer. Finally, the expression of the optical path difference for the central bright fringe is delta central bright fringe equal to 0. Now let's solve this application. Identifying the nature of a fringe, specify the nature of the fringe located at O, the point of intersection between the perpendicular bisector of S1, S2 and the screen. Given S is on the perpendicular bisector of S1, S2. To solve this application, we have to find delta at O. Delta at O equal to SS2O minus SS1O, which is equal to SS2 plus S2O minus SS1 plus S1O, equal to SS2 minus SS1 plus S2O minus S1O. And since S is equidistant from S1 and S2, so SS1 equal to SS2. Also, since O is equidistant from S1 and S2, then S1O equal to S2O. And finally, we get delta at O equal to 0. So at O, there is a central bright fringe. In this part, we have to find the expression of the position of the center of a bright fringe. For a bright fringe of order k, delta equal to k lambda, but delta equal SS2 minus SS1 plus AX over D. Delta equal to delta, implies SS2 minus SS1 plus AX over D equal to K lambda. So AX over D equal to K lambda plus SS1 minus SS2. Multiplying this expression by D over A, we get X of the kth bright fringe equal to K lambda D over A plus SS1 minus SS2 times D over A. Note, when the source S is equidistant from S1 and S2, so SS1 equal to SS2, so in the formula of the expression of the position of the center of the central bright fringe, SS1 and SS2 cancel each other and the position becomes K lambda D over A. Now the expression of the position of the center of a dark fringe. For a dark fringe of order K, delta equal to 2K plus 1 lambda over 2, but delta equal to SS2 minus SS1 plus AX over D. Delta equal to delta implies SS2 minus SS1 plus AX over D equal 2K plus 1 lambda over 2, and so AX over D equal 2K plus 1 lambda over 2 plus SS1 minus SS2. Multiplying this expression by D over A, we get X of the kth dark fringe equal to 2K plus 1 lambda over 2 A plus SS1 minus SS2 times D over A. Note, when SS1 equal to SS2, the expression of the position of the center of the kth dark fringe becomes 2K plus 1 times lambda D over 2A. Now we are going to determine the expression of the position of the central bright fringe. For a central bright fringe, delta is equal to 0, but delta equal to SS2 minus SS1 plus AX over D. By replacing delta in this expression, we get the position of the central bright fringe, which is equal to SS1 minus SS2 times D over A. Three cases may arise. First case, when the source is placed at the perpendicular bisector of S1, S2, then SS1 is equal to SS2, and so the position of the central bright fringe will be equal to 0, so the central bright fringe is located at O. The second case, when the source is shifted downward, as we see in the figure, then SS1 is greater than SS2, and so SS1 minus SS2 will be positive. Then the position of the central bright fringe will be positive, so the central bright fringe is displaced above O. Third case, when the source is shifted upward, then SS1 is less than SS2, and so SS1 minus SS2 will be negative, so the position X is negative, and so the central bright fringe is displaced below O. In the case of bright fringes, K equal to 0 corresponds to the central bright fringe, K equal to 1 corresponds to the first bright fringe above the central bright fringe, and when K equal minus 1, this corresponds to the first bright fringe below the central bright fringe, and so on. In the case of dark fringes, K equal to 0 corresponds to the first dark fringe above the central bright fringe. K equal to 1 corresponds to the second dark fringe above the central bright fringe, and K equal to 2 corresponds to the third dark fringe above the central bright fringe, and so on. But K equal minus 1 corresponds to the first dark fringe below the central bright fringe, K equal minus 2 corresponds to the second dark fringe below the central bright fringe, and so on. In this application, we have double slits illuminated by the source S of monochromatic light of wavelength lambda equal 600 nanometer. OI is the perpendicular bisector of S1, S2, and the point S is equidistant from S1 and S2. In this application, we have to specify the nature and the order of the fringes located at M in each of the following cases. You should note that in all parts, since SS2 minus SS1 equal to 0, delta will be equal to S2m minus S1m. Part 1. S2m minus S1m equal 3 micrometer. If m belongs to the center of a bright fringe, then delta should be equal to k lambda. So k equal to delta over lambda. Substituting delta and lambda, we get k equal to 5. Belong to z, so m belongs to the center of the fifth bright fringe above O. 2. S2m minus S1m equal minus 5.1 micrometer. If m belongs to the center of a bright fringe, then delta should be equal to k lambda and k equal to delta over lambda. Substituting delta and lambda, we get k equal minus 8.5, which doesn't belong to z, so m doesn't belong to the center of a bright fringe. So if m belongs to the center of a dark fringe, then delta should be equal to 2k plus 1 lambda over 2, and so minus 5.1 equal 2k plus 1 times 0.6 over 2. So finally we get k equal minus 9, which belong to z, so m belong to the center of the ninth dark fringe below O. 3. S2m minus S1m equal 2.1 micrometer. If m belong to the center of a bright fringe, we find k, which is equal to 3.5, doesn't belong to z, so m doesn't belong to a bright fringe. And if m belong to the center of a dark fringe, then delta should be equal to 2k plus 1 lambda over 2. We find that k equal 3 belong to z, so m belong to the center of the fourth dark fringe above O. 4. S2m minus S1m equal 1.6 micrometer. If m belong to the center of a bright fringe, then delta should be equal to k lambda. We find that k equal 2.67, which doesn't belong to that, so m doesn't belong to the center of a bright fringe. If m belong to the center of a dark fringe, then delta should be equal to 2k plus 1 lambda over 2. We find that k equal to 2.1667 doesn't belong to z, so m doesn't belong to the center of a dark fringe. So in this case, m is neither on the center of a bright fringe nor on the center of a dark fringe. In this part, we are going to define and determine the expression of the interfringe distance. By definition, the interfringe distance is the distance between the centers of two consecutive fringes of same nature. The expression of I equal xk plus 1 minus xk. For a bright fringe, xk equal to k lambda d over a, and xk plus 1 equal to k plus 1 lambda d over a. I equal xk plus 1 minus xk. By substituting xk plus 1 and xk, we get I equal lambda d over a. Similarly, for a dark fringe, I equal xk plus 1 minus xk. By substituting xk plus 1 and xk for a dark fringe, we get I equal lambda d over a. Now let's solve the following application. The distance between the centers of the forest bright fringes of 10 bright fringes extends over a distance of 2.25 centimeters. Determine I. You should know that between 10 bright fringes there is 9 interfringe distance, so d is equal to 9i, and then I equal d over 9, so I equal to 0.25 centimeters. Now let's solve application 5. In Young's double slit experiment, the distance between the centers of the second bright fringe and the seventh dark fringe is d equal 0.9 centimeter. Determine I. You should remember that x of the kth bright fringe equal to k lambda d over a. The second bright fringe is of order k equal to 2, so x of the second bright fringe equal 2 lambda d over a, but I equal lambda d over a, and so x of the second bright fringe equal to 2i. And you should notice that x of the kth dark fringe equal to 2k plus 1 lambda d over 2a, and the 7th dark fringe is of order k equal 6, so x of the 7th dark fringe equal 13 lambda d over 2a, so it is equal to 13 over 2i equal to 6.5 I. D is equal to x of the 7th dark fringe minus x of the 2nd bright fringe equal to 6.5 I minus 2i equal to 4.5 I, and then I equal to d over 4.5 equals 0.9 over 4.5, so I equals 0.2 centimeters. Now try to solve exercises 6, 7, 9, 10, 11 and 12 on page 254 on your official book, or pause the video and try to solve them. This is the end of part 1. Please watch part 2 next. Thank you for watching our videos. Please don't forget to subscribe and press the bell icon for latest updates.